Remember, supernova explosions throw newly produced elements and isotopes into the interstellar space. Now, how does this material make its way into new stars, or how did it do so into the solar system and Earth 4.5 billion years ago? Like that? Astronomers need to trace the flows of freshly produced nuclei through interstellar space, right? Think of how in medical exams the flow of materials within your body are traced through a contrast agent. This is ingested into your veins or into your stomach, and it contains radioactivity. In this case, this is fastly decaying, for the example of the isotope of iodine-123 within half a day. And radioactivity is matter that shines in characteristic radiation as it decays. So a machine takes a tomography scan in high energy radiation, and the computer then can image how this material flows within your body. And we astronomers, we use exactly the same method. Nuclear fusion inside stars produces a tiny little bit of radioactive materials alongside with other new nuclei. And we can use these to trace the cosmic flows, such as from a supernova to other places many light years away. I will show you some interesting maps. But first, let's look at how we can measure the radiation from cosmic radioactivity. Atomic nuclei are tiny, and they are largely empty space, as the electrons orbit around a nucleus to form a shell whose overlaps make the chemical bonds. Now, atoms have a characteristic size smaller than nanometers. That's 1/10,000th of 1/1,000,000th of a meter. And the nucleus of an atom is 10,000 times smaller still. Light always has typical wavelengths of the microscopic objects which emits it. So, from the atomic shells, we get light at nanometer wavelengths. And this is where our eyes can see, and it appears colorful to us. Candlelight is yellowish. The sun is whitish. Radioactivity happens inside an atomic nucleus, so its characteristic radiation has a much smaller wavelength, which is similar to that dimension. This radiation is called gamma radiation. So when we astronomers aim to trace cosmic radioactivity as it flows, we must image gamma rays. How do our astronomical telescope capture cosmic light anyway? In an optical telescope, a mirror bounces the photons that come from distant stars and explosions onto a light detector. The bigger the mirror is, the more light can be collected through such bouncing onto a light detector. And this light detector is a chip, just like what you have in your imaging cell phone. Collecting with 10-meter-sized mirrors is how astronomers can see light from very distant and faint objects. Now, what if the wavelength gets smaller, like for blue or ultraviolet light? Now, the mirror surface quality really matters. We have this bouncing, so as the wavelengths get shorter, the mirrors still bounce if we polish them smoothly, but not as regularly and as reliable, when small scratches or grains remain on the surface. So what about smaller wavelengths when we get into the size regime of atom separations of nanometers? See, here comes a situation where the X and gamma ray photons can fall through the surface between the atoms. For the shorter wavelengths of gamma rays, mirrors don't work anymore. Ooh! Now, there is no collection from a larger area with mirrors. We only have the photons that directly hit our detector itself. Therefore, collecting gamma rays takes much more time with such little collection area, and many of the gamma rays even penetrating our detector itself. This means it's difficult to see faint sources far away. These telescopes for gamma rays, they look different. They are complexes of photon detectors collecting each of these precious photons one by one. This looks more like something you may associate it with CERN's particle detectors. But these gamma-ray telescopes also work. This kind of astronomy is only 50 years old compared to the astronomy that is 400 years old. Here is a result of how the gamma-ray sky looks like in gamma rays. This is our Milky Way galaxy, but in the characteristic radiation of the radioactive isotope 26 of aluminum, radiating as it decays. This is different from the maps of the stars in our galaxy, where we can see nearby stars and interstellar clouds block more distant views, or in the infrared, where we can see through those dust clouds and we can see the inner region of the galaxy with its many low-mass stars. The radioactive glow is not coming from stars. It is diffuse. It comes from the space between the stars. The isotope that shines here has a radioactive lifetime of 1,000,000 years. This seems long, but it's 10,000 times shorter than the age of our galaxy. So we see material that must have been produced and ejected from nuclear fusion places within the past 1,000,000 years. It is the collective glow from many such explosions occurring at different places here and there, but everywhere along our Milky Way galaxy. This amount is as much mass as our entire Sun has, and all in just one isotope that is a tiny byproduct of nuclear fusion. We can see it, and we have an image of the flow of newly produced nuclei through interstellar space in our galaxy. This would be equivalent in mass of more than 10 to the 30 cups of cream. Yes, we can trace how newly produced nuclei move around in our galaxy. With gamma rays, we can also look at explosions in the cosmos just as they happen. And this you will see in the next episode of the Astronuclear Nibbles.